Here in this video, we want to look at different real-life situations where we need to know whether we apply a linear model or an exponential model to model the evolution of a certain quantity in the problem. So we're going to look at three cases. So case number one, we've got the population of Canada, which is 38 millions. That's pretty much what it is currently, and it grows by, and I just made that up by the way, it grows by 0.5 millions per year. So 0.5 millions is, I made it up. The 38 I'm pretty sure of. So what's going on here? Well, if we've got P of t, okay, which is population at time t, okay, currently it's 38, okay, so when t is 0, and then we're basically adding 0.5 every year. So we multiply 0.5 by t, and we see from this that we have a linear model for the population. So that's going to occur if we look at how delta p changes. It changes by 0.5 when the change in time is 1 year. So every year it goes up by 0.5 million. So as you can see that the change here for an increment of 1 will always be 0.5. So overall, if over equal increments of time the increase is always constant, we get a linear model. Okay, so of course if the increment now is 2, so if over equal increments of 2 years, the population is going to grow by 1. Okay, but it's still constant if this increment is constant. Okay, so this is when you know you have a linear model. So over equal increments of time, the increase is constant. So in other words, the rate of change is constant. Okay, so that means delta p over delta t is a constant. Now let's take a look at, so maybe something to frame here. It's kind of important. So this is how you're going to tell you've got a linear model to implement. But let's look at the second example. Now we've got the population of India, which is 1.3 billion and grows by 1.3% each year. So you realize that each year it's going to be a little more because 1.3% of the current amount is going to be less than 1.3% of the amount of people 1 year from now. So we don't have a constant increase every year. Okay, it's actually going to get larger and larger. So here, over equal increments of time, the increase, it's not a constant, but it's the same percentage. So if you see that the increase is a percentage of the current amount, then that's likely to be an exponential model. Same percentage. Let me spell that correctly. Okay. So in other words, delta p is going to be 1.3% of p, same percentage of p, when or p of t if you prefer, when delta t is 1. Okay, so over equal increments of time, it's always delta p is always going to be 1.3% of p of t. So if it would just be 1.3%, that's a linear model, but it's 1.3% of the population. Okay, and that makes it nonlinear because that's likely to change as p of t changes. Here, that's going to lead us to a model that's like that. So initially we've got 1.3 billion, and this is like our interest rate problem. So we're adding 1 and so 1 plus 1.3%. Okay, so in other words, what is that? That's 1.013. Right? 0.13 is 1.3%. And that's going to get multiplied. Well, multiplied by itself, so it's going to be raised to the power of t. Okay, just like our money in the bank account. So this is also something you want to frame. This is how you detect that you have an exponential model. Sometimes it's presented differently. For example, there are 10 rabbits and the population doubles every month. Okay, doubles, what does that mean? It means it's 100% more than what it was before. Okay, so this is an increase of 100% of the previous amount. Okay, so it's going to be 10, so the population. Okay, so here t is in month, t in months, right? Where before for India it was t was in years. Okay, and for Canada, what was it again? Canada per year. So that was actually t in years. So here it's 10, and then basically you do 1 plus 100%. Okay, to the power t, but 100% is just 1. So this is 2 here. 1 plus 1, 2. So it's going to be 10 times 2 to the t. And that's the model here. So doubles every month. If it triples every month, then it would be plus 300%, right? And then it'd be 4. Sorry, I just said something that's false. If it triples, it's plus 200%. For example, let's say it's 10. If it triples, it would be 30 after a month, 90 after 2 months, and then it triples. Okay, so you're adding 20. 20 is 200% of 10, and then you're adding 60, which is 200% of 30. So then that would lead to 10 times 3 to the t. Okay. For example, when t is 1, you get 10 times 3, you get 30. When t is 2, you get 10 times 9, which is 90, so it works. Okay, so you just have to watch out for those. If it's something like that's doubles every year, or that's half of what it was every year or every month, it's going to lead to an exponential model. If it's phrased in terms of a percentage of the current amount, that's also an exponential model. But if it's constant for over the same increments, then in that case it's linear. And quickly take a look at another example that's kind of similar to what I just did with populations, but now it's a company that produces. We have got 2 companies that produces stores. Okay, so if you start at the second sentence above, company A has 100 stores and expands by opening 50 new stores a year. So you see every year, okay, it's 50 more. So that's constant. So that tells you, oh, it's going to be a linear model. So we start at 100 and essentially we go up with a slope of 50. So this is why they write a of x is 100 plus 50x. Okay, so it's a linear model that models how that company produces stores. But company B, look, it has 100 stores and expands by increasing the number of stores by 50% each year. So this is going to be, this increase is going to depend on how much store you've produced the previous year. So here it's an increase of 50%. It's a percentage, and therefore it's going to lead to an exponential model. So you see b of x is 100, which will multiply by 1 plus 0.5, 0.5 as in 50%, to the power x. And you can compare in the table like how many, like depending on the number of years that have gone by, how much stores are produced by company A and company B. You can also look at their graphs. So for company A, of course, it's a straight line with a slope of 50. They both start with 100, but look at company B. it's an exponential model, and you see that curve shooting upwards. It's not a parabola, by the way. It's really a different kind of curve. It actually goes faster than a parabola towards infinity. And this is where the base is 1 plus 0.5. So it's 1.5, and that's why it's increasing. So 1.5 being above 1, you get a graph that's increasing like this. You actually can see that just over the first year. You can actually kind of tell if you zoom here. I don't know if we can see it, but the blue curve is slightly below actually the line, the red line. So it's actually producing less stores during that first year, and then after 1 year, it's the same amount, 150, and then after that, company B produces more stores.